Hello everyone, welcome back to the latest lecture session. In the last couple of sessions, more or less we have been looking at aspects that have come into play relatively recently, at least in India. For example, we started discussing adsorption, right? And in general, we haven't applied adsorption in wastewater treatment a lot, at least in the Indian context, but with various requirements and such, they are coming into play, at least those aspects that look into or use the principles given in adsorption. One obvious example was granular activated carbon. In that context, obviously, activated carbon has some active sites which can adsorb my organic compounds of interest, right? And after all these sites have been exhausted, I need to replace the relevant activated carbon. In that context, I believe we looked at breakthrough, right? Granular activated carbon and breakthrough, right? So, this is the mass transfer zone here, yes, and I guess here it is the mass transfer zone here, and so on and so forth. So, what is happening? I guess we did discuss this. So, here this part of the adsorbent, there are no more sites available for adsorption, and now I guess the active mass transfer zone is out here. So, this profile has some relevance, we will look at that. For example, this is the breakthrough, and this corresponds to, or this particular graph corresponds to the profile that we see out here. So, if my inlet concentration is, let us say here they say 101, I guess let us say just for sake of it 150 milligram per liter of the compound of interest, and I do not want the concentration to be greater than 10 milligram per liter, okay, 10 milligram per liter. And so, during all this time, this is time, operation time, it is fine. But obviously, here the concentration is reaching my acceptable level, the concentration in the effluent, and then it is beyond the concentration that I am comfortable with. So, I guess I would say that the system has achieved breakthrough here itself, right. So, that is something to keep in mind. But what will decide the shape of this particular tail or such, if I may call that, or shape of this particular breakthrough, right. Let us look at that aspect. So, before we go further, I guess we did look at it in the context of some of the other aspects there with respect to the isotherms. Typically, we have favorable and unfavorable isotherms. So, here it is Q, and I guess you have amount adsorbed per unit weight of adsorbent, and here pressure, but we will look at it in terms of concentration in the liquid, right. So, here as you can see at maximum capacity, I guess, or maximum concentration, fine, the capacity is the same at maximum concentration though, right. But if I look at the cases when the concentration is somewhere out here, let us see, right, the concentration at or in the aqueous phase, right. What do you see? We see that there for the same equilibrium Q or C, pardon me, what do we see for the favorable one? We see that more amount is adsorbed per unit weight of the adsorbent. For this, we see that relatively less amount is adsorbed per unit weight of adsorbent. Why is that relevant? Well, if my adsorbent can adsorb more of the compound of interest, even at the given concentration in the aqueous phase, right, we are talking about that particular equilibrium conditions at that particular concentration, it means that with less amount of adsorbent, I can adsorb more of the compound, right. So, the volume or the mass of the adsorbent required will be relatively less. But with the adsorbent that follows the unfavorable isotherm or such, the shape that we have here, what will you see there, or what would you observe there? Obviously, you need a lot of adsorbent to be able to achieve that given amount of contaminant removal, let us say. That is something to keep in mind. Again, some of the concepts here that we are going to discuss, I was able to clear by talking to Dr. Sudipta Sarkar. So, thanks to him. So, that is in general, right. Again, extreme case of favorable, irreversible, but rarely will we see that particular case, favorable and unfavorable. This is one aspect to keep in mind. And in what context were we discussing this or trying to discuss this regarding this breakthrough curve, let us say. So, here the same graph, if I am trying to plot it here, right, this is time, let us say, and this is the concentration in the effluent, let us say. So, the profile can be like this, a relatively sharper breakthrough, right, or it can be, or it can take a different shape too, right. For example, it can be something like this. So, if I look at the acceptable concentration or the levels that I am comfortable with, here you see that the breakthrough has occurred earlier, and for the other case we see that the breakthrough has occurred later, T1 and T2. This is the concentration, let us say, that I am fine with, comfortable with. Yes. And how or what factors decide this particular what do we say, shape of the curve? Let us look at that. So, one aspect is that the concentration velocity, as in this particular, let us say we are having 150 here, right. Let us say, let us consider 100 milligram per liter, that zone at which the concentration is 100 milligram per liter. Over time, obviously it is moving down, right. In this case it is moving down. So, if I look at that as concentration velocity, looks like it is dependent upon 1 by, I guess you have terms with respect to porosity, Q by A and such, yes. And in the denominator though, what is it that I am going to have? This is concentration velocity, right, concentration velocity. I am going to have 1 by dq by dc, right. This is, in a way, you have q and c here, right. Okay, we have q and we have c here. So, for the favorable, let us look at two cases. Let us say one case is out here, when the system is in equilibrium with higher concentration, right, that is one case, yes. And another case is here, let us see, when it is in equilibrium with lower concentration, right. So, this is one aspect, yes. So, as you can see, slope relatively flatter, relatively steep here, and as we mentioned or looked at earlier, we have this concentration velocity to be proportional to 1 by dq by dc. Again, there are other terms, q by a, which is the superficial velocity, I guess, or the flow velocity, and also porosity here, dq by dc. So, as you can see here, let us say relatively lesser value here, right. So, case 1, let me write that here, and case 2. So, in that context, what we will have? I will have 1 by a smaller value. I am saying this is case 1, this is case 2, right. So, case 1, 1 by smaller value, meaning Vc will be relatively high, right. And in case 2, slope is steeper. So, again coming back to this particular case, 1 by dq by dc is higher. So, Vc will be relatively lower, right. So, case 1 and case 2. Why is this relevant? As we were looking at it here, when it is coming in this direction, what is happening here? So, this phase will be in equilibrium or in contact with, or it will be more or less case 1 here, right. And what about case 2, right, when it is somewhere out here, yes. So, case 2 is relatively slow, right, case 2 is somewhere out here. So, as you can see, 1 is relatively fast, okay, let me write it here, 1 is relatively fast, 2 is relatively slow. That is what we see. The leading edge or the head, which is in equilibrium with relatively lesser concentration, is relatively slow, but the one or the tail, I am using layman's term here, that is relatively fast. So, what happens? This mass transfer zone will be relatively less. Then the kind of breakthrough that you will have, let us see if I have a blank slide here. So, the kind of breakthrough that you would have, right, this is the profile. So, the mass transfer zone is relatively less, right. So, here and here, I guess, right. So, this is the mass transfer zone. So, that is relatively less. So, then I will have a sharper breakthrough whenever the breakthrough occurs, right. So, that is the case. But if it is the case with the unfavorable isotherm, so this was the case when we looked at the favorable isotherm. If it is the case for unfavorable isotherm, what is going to happen? The reverse is going to happen. Here we looked at case 1 and case 2, or yes, and Vc1 was relatively faster, Vc2 was relatively slower. But in this case, you can look at the slope, what is going to happen? So, at 2 and here 1, Vc1 is relatively slower, Vc2 is relatively faster. Again, you can look at the relevant slope here at different cases, let us see, right. And so, what does that mean? I am going to have this kind of a shape where the mass transfer zone is like this, right, or the shape which is similar to what we had here, let us see, right. So, that is the relevant aspect here, right, something like this. So, what is that going to lead to? Whenever breakthrough is about to occur, will I have such a sharp breakthrough? No, I will have something like this, right. So, I will have something like this and this elongated or this kind of tail shaped breakthrough, right. So, as you can see, if I had a sharper breakthrough, that would have occurred later, yes, even though the capacity is the same. So, you see my breakthrough time is relatively lesser. So, again that is one aspect to keep in mind or consider. So, enough of this aspect for now. Let us move on to the next aspect. So, as I mentioned, we are going to look at ion exchange, right. So, again here the principle is ion exchange, right. I am going to exchange one ion for the other. Let us go about and see what it is that we have. So, as I just mentioned, ions from the solution adsorb onto solid. At the same time, an equivalent amount of ion is released. Keep in mind that we are talking about equivalents with respect to the charge. Typically here we are talking about ion exchange and charge, right. Earlier it was adsorption, as in I had just had activated carbon, typically hydrophobicity. The compound does not want to stay in water, it comes and adsorbed onto my activated carbon. There was no exchange there, right, it was just adsorption. So, here though we are going to have ions being exchanged, as in something is going to be present on my media, right, or my backbone or the resin, and that is going to be exchanged for another ion. Why there is going to be an issue here or aspect here, we will look at that. So, let us move on. Material to which ions are sorbed, right, in exchange for ions already bound to the exchanger. Material to which certain ions are sorbed in exchange for ions already bound to the exchanger, right. So, example, what is it that I have in water? I have calcium and magnesium, and these I want to remove. They will have Ca2 plus and Mg2 plus charge, and the one in the resin has Na plus charge. So, due to the relevant affinity for calcium and magnesium, due to the relevant hydrated radius, we will come back to that later. The resin strongly prefers to have calcium and magnesium rather than Na plus. So, Na plus will be released into the solution, while calcium and magnesium which are in the solution will be adsorbed onto the resin, right. So, that is one aspect to keep in mind, right. Okay, I guess that is the relevant aspect I have here, right. So, I have calcium in the solution, and here is the ion exchanger, right. Ex is the layman's term that we are using to denote anion exchanger, cation exchanger, and then 2 sodium are replaced for 1 calcium. Obviously, why? 2 plus charge on this and 1 plus charge on this, right. So, let us see same case with magnesium. Fine. We have components. I guess we did look at this. So, we have the resins and manifolds and such, but again I just wanted to present a relevant picture. Again, keep in mind that you will again have to regenerate it and such, either on site or off site. So, that is one aspect to keep in mind, but let me not dwell a lot of time or spend a lot of time on this picture. So, multi-column ion exchange. So, I guess you see different columns and such out here, yes, and this is what it can typically look like. Let us see. So, characteristics of material and such, let us look at what it is. So, what are we looking for? We want to have a surface charge that attracts the oppositely charged ions, let us see. So, cation exchange resin, let us see, right. So, it will have a negative charge, and that is why H plus is relatively bound to it, right, or adsorbed onto it, and then Na plus comes into the picture, and depending upon the relevant affinity, it will replace or exchange with H plus, let us see, right. So, that is something to keep in mind. Negative charge obviously attracts positive ions, that is why it is called a cation exchanger. So, as you can see, cation exchange, Na plus cation positively charged, H plus cation. So, we have a cation exchange taking place. So, what does it typically look like? Let us see what we have here. So, this is the initial case and this is the case at equilibrium. So, what do I have? I have B plus and X minus compounds, right. In water you have to have charge neutrality, that is why you will always have the cation and the relevant anion, let us see, right. So, you have aqueous phase ions which we want to remove. I want to remove B plus, fine. I want to remove B plus, and in the resin obviously has a negative charge, yes, and again even it has to be balanced with respect to charge, and that is why you have the ions here, right, the relevant positively charged ions, yes. So, what is going to happen? Because the resin has a greater affinity for B plus rather than A plus, what are you going to see? You see that B plus is going to be adsorbed onto the resin, while A plus is going to be released. So, here I am going to have ion exchange. So, at equilibrium you see that most of the B plus has been removed, right. Again, it is an equilibrium, that is why I guess you can't have 0, you will be relatively, you will have relatively less, but you will not have 0. So, that is what you see out here, right. So, types of ion exchangers, we have natural materials like soils, typically they will have cation exchange capacity. Why is this? Due to the negatively charged, typical negative charge on the clays, let us say, that is one aspect to keep in mind. And zeolites, again they are were originally used in water treatment, and even now a lot of research goes into zeolites. These are the natural materials, right. And we have moved on, or quite a few people now look at applications of synthetic resins, right. So, we have synthetic ion exchange resins. What do these resins contain? Obviously, we need a polymer backbone, right, that is one aspect. And to interlink or link these backbones, you are going to have cross linking groups. And obviously, for the exchange, you need the exchange groups, right. One is the backbone, one to cross link or interlink, and one is the exchange group, I guess, right. So, let us look at a picture. So, here I guess we have the relevant picture. So, here you see the backbone, right, that is coming from here, and here this is the cross linking group, right. So, this is the cross linking group here, divinyl benzene there, and here also divinyl benzene. So, two cases here. Here styrene is the backbone, or leads to the backbone, I guess, okay, resin backbone, as you can see, yes. And here it is methacrylic acid, right. You can see the backbone, and then the interlinking between what we say different chains based on this particular cross linking, right. And as mentioned, exchange groups, right. So, exchange groups, so COOH, right, RCOOH, let us say it can be as plus H plus. So, it can release this H plus, right. So, thus you will have that particular what do we say, this particular site is the exchange site, and here again SO3H. So, H plus can be released and the relevant cation can be absorbed here, right. So, you are going to have ion exchange, right. This is one aspect to keep in mind. So, synthetic exchange groups, what else do we have? Negatively charged, right. So, they will be cation exchangers. So, again in the context of these exchange groups, we have a concept about strong or weak acid resin. We will look at what it is about in just a moment. So, here we have, as we just looked at, right, carboxyl groups RCOH, again with and without the proton, sulfonic, yes. So, thus if you can remember or look at your acid base relevant aspects, right, we have this type of a curve for acids and bases, yes, and this is the protonated form HA. HA, let us say, is this form, and this is the A minus, right, deprotonated form. And we have x axis here, we have the concentration here on the y axis. As you can see, the kind of compound that is going to be present is going to be dependent upon the pH, and this particular what we say point at which the concentrations are equal is pKa, right, acid dissociation constant. So, if pH is greater than pKa, pKa is a constant based on that particular compound, again from the equilibrium constant. If pH is greater than pKa, for example here, what does it or which form is going to predominate? This particular form A minus, right, A minus is going to predominate. But if it is going to be present when the pH is less than pKa, which form is going to be predominant? Obviously He. So, the issue here is when the compound wants to stay as or in its protonated form HA, then obviously it is not going to function as an ion exchanger. So, obviously as you can see, pH plays a considerably important role. When will this be important? This will be important for weak acid resins. Weak acid, when do we say or call a particular compound or an acid as weak acid? When the pKa is relatively high, not relatively low, let us say, right. So, that an example of that is this carboxyl, right. And I guess this was discussed in the context of acetic acid and such. We looked at some examples in the context of acid base chemistry we looked at earlier. So, here also one aspect to keep in mind is that the capacity, right, the total capacity also increases depending on pH. If the pH is here, obviously capacity is less, because while a significant fraction are present as A minus, a significant fraction is still present as, most of it is present as HA. But if pH of the solution is here, right, relatively further from the pKa, what do you see? Most of the most of the compound is present as A minus or would want to be, and only some of it will be present as the protonated form. So, greater sites are available for ion exchange. For sulfonic, this pKa which is out here, the pKa will be somewhere out here, let us say, right. pKa will be somewhere out here. So, at almost all pH range, it can act as an cation exchanger. That is why we call this as a strong acid resin. Again, there are advantages and disadvantages depending upon which cases you want to look at, but we will not go into that now. Again, different other kinds of cation exchangers. Obviously, if I have cation exchanger, I will also have anion exchanger. Anion negatively charged, so the resin needs to have a positive charge, right. Similarly, as we just had strong and weak acid resins, we are also going to have strong or weak base resins, right. Similar concept as above. So, amines typically quaternary amines, right. So, that is one thing to keep at or look at, NH4 plus, right. So, you are going to replace the H here, right. So, that is something to keep in mind. So, let us just summarize this or understand this. So, strong acid cationic resin, typically sulfonates, relatively low pKa. That is why the operating range is, pretty much starting from 1, pH 1, right, greater than 1, let us say, right. And regenerant, okay, we will come back to this. We want to regenerate it, that is the relevant aspect too. So, the type of ions it can remove. And weak acid resin carboxylate, as you can see, it is operational only beyond its pKa, right. So, I guess we are looking at relevant pKa, and then we will understand the kind of range where it is going to be functional at. Same case, as you can see, strong base, more wider range, weak base, depending on the pKa, it is going to be able to exchange, right, the relevant anions only when the pH is less than 6. So, you can see depending upon your solution pH which one is more acceptable and not. And one aspect to note is that because the weak acid resin, let us say, let us look at this weak acid cationic resin at a particular pH, you know that it wants to have the proton H plus. So, when you are regenerating it, as in consider the case when all the ion exchange sites or most of them have been taken up by your compound of interest that you want to remove, but you do not want to throw the resin out, right. Then it is a considerable cost, and also you are going to look at what do I need to do with that particular resin. So, you will regenerate the resin. How will you do that? Well, it is like reversible reaction, you can think of that partially. Let us not go into the details here. So, I will add a lot of H plus, right. But with respect to the strong acid, as you can see, it does not have a great affinity for H plus. It tries to release H plus because its pKa is pretty low. But for weak acid, pKa is relatively high. At a considerable range, you know that it strongly wants to take up H plus. So, it is easier to regenerate the weak acid cationic resin compared to the strong acid cationic resin, right. That is one aspect to keep in mind. Let us move on. So, I guess we looked at this, but let me just summarize again. The bead here is polystyrene polymer cross-linked with divinyl benzene. This is what we looked at earlier, right. So, we have cross-linking here. The cross-linking is due to divinyl benzene, the structure of which we looked at earlier, and here we have polystyrene polymers, I guess, right, polymer chains. I guess this is the macroscopic view which you are now looking at. Earlier we looked at the relevant compounds and such, right, with the fixed coions, right, minus charge balanced by mobile positively charged counter ions. So, the counter ions, so this is the mobile counter ion. For example, Na plus is the counter ion and Ca2 plus will be exchanged with this counter ion, let us say. The fixed ion is giving the relevant charge which is the negative charge to this particular weak acid resin, let us say, right. Because it has a negative charge, fixed negative charge, it will obviously have opposite counter ion, let us say, right, the counter ion there. So, that is what we are looking at here. So, strong cation exchange resin on the left and strong base on the right. Again, this is depend obviously on the pKa value of the relevant group. That is something to keep in mind, right. So, let us move on. And what does it actually look like? Here you see the relevant beads and the diameter is 75 to 150 micron. Obviously, as you can see, it is relatively small. Depending upon your functionality and also the increase in volume during ion exchange, you can have or look at different kinds of sizes. Here we have relatively bigger diameter, 500 to 590 micrometer. I just wanted to present a picture so that you can understand the kind of or how it looks like, right. So again, ion exchange wave saturation, we looked at this in the context of adsorption. So I will not look at that or go through this in detail, let's say, but let's just summarize that. For a column of resin, the exchange reactions begin to saturate the upper levels, right? Initially, we are going to have saturation here before the lower levels, yes. And then I guess we'll use the term mass transfer zone earlier. The progress of this saturation through the column results in a wave of saturation. For example, in the earlier context, we looked at something like this wave, right? So this has been saturated, this has not been saturated yet. So that is what we can look at. For example, this whole part has been saturated here, here relatively bigger part at this part, here almost none of it has been saturated, right? So that's what we are talking about. So the exchange zone has been highlighted here. This is moving through. So once it reaches down, and depending on your concentration, you are going to have relevant breakthrough, right? So let's look at it here again. So we have, what do we say, inlet concentration C naught and effluent concentration Ca. Ca is below the relevant concentration that I am looking at, so that is fine. So what do we have here? So initially we have a lot of active sites or ion exchange sites available, right? And thus most of the cations are being taken up, let's say. But as we move further down, you see that almost all the sites are being used up. And at this particular point, we have the breakthrough. Why are we calling it the breakthrough? Because my particular concentration of interest has been crossed by the effluent concentration. As you can see here, mass transfer zone has reached this, or exchange zone has reached my outlet. So the concentration of the relevant compound in the outlet is going to be higher. And if it's higher than the compound or the standard of interest to me, then I'm going to call that the breakthrough. And this breakthrough, I guess, is here when it reaches this particular effluent. So again, this shape and such, we looked at it earlier, let's not go into that. So again, as we mentioned, it's, you can represent it as a kind of reaction. So here we have the resin, and this is the ion in the water, right? And now A plus is being exchanged with this Bn plus, let's see, yes. So you can write it in terms of, you know, the equilibrium constant, right? You have the products in the numerator, and in the denominator you are going to have the reactants. So that's what you have out here, let's see. So if you want to have this reaction going forward, what do you want to have? You want to have more of this. If you want to have this reaction go forward, the backward reaction, what do you want to have? You want to increase the concentration of A plus. This is the principle for regeneration too, right? Again, let's not look at that right now. Okay, let me skip this because we discussed this. So selectivity of ions. So we looked at, you know, Na plus or H plus, you know, as the initial counter ions, right, or the counter ions. And why is it that they will be replaced by the calcium or magnesium in my particular solution? Why? Right. So here we are going to talk about selectivity of ions. So we have preference of the ion exchange material for one ion over the another. So here we have again a particular variable called the selectivity coefficient, right? Again, S and R denote the solution and resin concentration and such. If we have Qs equal to 1, no preference for A over B, right? If Qs is greater than 1, obviously Bn plus 1 is going to be preferred over A plus, right? That's what we want. Qs is less than 1, again you can look at this. A plus is preferred over Bn plus 1. If Qs is greater than 1, what does that mean? That means that the denominator is higher, right? We obviously had this particular equation here, right? If this numerator, even if it's not at equilibrium, so this is Q, let's say, right? So what does it mean when the numerator is higher? It means that the system prefers that A plus is in the solution and B plus is adsorbed, or, you know, is with the relevant co-ion there, right? So this means that it has an affinity for the B plus. If not, if Q is less than 1, I guess denominator is relatively higher. What does it mean? This particular resin has a greater affinity for A plus, right? So that's what we are talking about. Let's move on. So stronger, so again selectivity, stronger attraction to multiple charged ions Ca2 plus than singly charged. Okay, fine. Why is this? The whole principle is that you are going to have ions, let's say calcium, and you know you are going to have its unhydrated radius, right? Another aspect is the hydrated radius, as in you are going to have, again water is polar, you are going to have some of these water molecules surrounding this particular calcium ion. So whenever calcium ion moves, these water molecules move with it. So when this calcium ion is being, what do we say, exchanged with Na plus, right? The system prefers one that has, I guess, relatively smaller hydrated radius, if I am not wrong. We will look at that, but again, smaller hydrated radius. Why is that? Osmotic pressure will be applied on the resin, and the system will see to it that the one that has less resistance, layman's terms, or less osmotic pressure will be taken in. So that's why those compounds or ions, pardon me, with lesser hydrated radius will be preferred. And typically, when will that be the case? When it's relatively smaller ion with greater charge, let's say, right? So bigger the ion and lesser the charge, your affinity typically decreases. Why? Again, it's relevant to the hydrated radius, right? So strong attraction for smaller hydrated radius, and typically it's inversely proportional to the unhydrated radius, as I just mentioned. So here obviously Ba2 plus Sr2 plus greater the affinity, I guess, right? This is for cations and this is for anions, but this is the general rule. There will be some aspects of here and there, but again, key aspect is to understand that it's the hydrated radius. So if we choose a resin with high affinity for the compound of interest, why is that going to be relevant? Obviously sharper breakthrough, then leading to shorter ion exchange column, and then obviously I can have greater flow rate, right? And disadvantages, obviously, if my relevant resin has great affinity for the compound that I am trying to remove, later when I am trying to regenerate this particular resin, obviously it's going to be relatively difficult. Why is that? Because it likes the compound so much, right? So that's one aspect to look into. So ion exchange capacity, we have two terms here. One is the total capacity and another is the capacity for the target ion. The key obviously is that one aspect deals with the target ion, one is about the total capacity. So for example, we were trying to, let's say, remove different compounds, let's see, yes, and we have calcium, fine. So if my target is calcium, but I have other cations that are present, my particular resin will not only pick up Ca2 plus, it will also, exchange or, have an exchange with the other cations present in the solution depending on the relevant affinities and such. So here I am going to be concerned about total capacity and also capacity for the target ion. So all possible exchange sites, units typically equivalents per gram or equivalents per liter. Typically I am having or looking at 1 to 4 milli equivalent per milliliter. For the target ion, obviously it's the total capacity minus capacity used for preferred ions, let's say, right, at breakthrough. So that's how we are going to look at it. Operation capacity depends on flow through the column, bed depth, right, bed depth, selectivity coefficient, exchange ion size, yes, again this is slightly relevant to the selectivity coefficient, amount of regeneration used, let's say, or extent of regeneration required. Why is this? Because the more regenerant that's used, again the costs are going to add up. Why? Because later again you have to dispose this regenerant somewhere. So relatively less volume, relatively less disposal cost too, and also even to get the regenerant you are going to, what do we say, spend less, right? So that's something to keep in mind. Composition and concentration of the feed solution, as in what's coming in. Why is that? If it's just Ca2 plus and I just want to remove Ca2 plus, fine. But if I have other compounds of interest, let's say with greater charge and such, right, let's say there is Fe3 plus, well I don't think there will be, and assuming that the affinity is relatively higher than Ca2 plus. So what's going to happen? The ion exchange resin will take up both Ca2 plus and Fe3 plus, right. So the composition and concentration of the field solutions come into play, and obviously again temperature, because again everything is about equilibrium constant and such, which is dependent upon the relevant temperature. And if when I say desired quality of water, we know that we are talking about breakthrough, right. If my desired quality of water is somewhere out here, low concentration, I'll have one particular operating time. If my breakthrough is relatively later, or if I can accept relatively higher concentration of the compound in my outlet, I'm going to have a different breakthrough time, right. These are the aspects that come into play. And one aspect to note when people come up with this different kinds of ion exchangers and such is the affinity. As in, fine, my resin can remove the calcium or the compound of interest, right, or chromium and such, but what about all the other ions that are also going to be present in the solution? So we obviously have to look at that data too, as in the selectivity for that particular compound, especially when we consider the background concentration of the other what do we say, competition which is from the other cations or such. We are talking about Ca2 plus. For example, people typically conduct experiments only on that particular ion of interest and say, hey, it's 100% removal. But if it's actual water, you are going to have other ions too, right? And these ions are also going to compete for these ion exchange sites, especially because these other ions will be at higher concentration. The compound of interest which you want to remove, which is toxic, will be typically at relatively low concentration. So then you have to look at these aspects, right? Let's move on. So ion exchange, where do we use that? Obviously softening, removal of calcium and magnesium, right? Na exchange and regenerate with NaCl, let's see, right? Nitrate removal, again Cl minus is exchanged, nitrate is NO3 minus, and again you are regenerating with NaCl. So perchlorate, very stable, right? Again Cl minus exchange depends upon the kind of charge, Ca2 plus and Mg2 plus, obviously Na plus or H plus exchange. And with respect to the anions nitrate and perchlorate, we are going to have Cl minus exchange and regenerate with NaCl. So toxic metal removal, like for example lead and mercury, we are going to look at regeneration with HCl. Why is it? To keep the pH low, to keep the metals in solution. If the pH is high, again you are going to have precipitation of these metals and such. That is not what you want, right? You do not want precipitation to occur, right? That is something you want to avoid. That is why I guess we are looking at HCl, right? Demineralization, OH and H forms regenerate with NaOH and HCl, let us see, right? I want to remove the minerals, right? It is all minerals. I am not just talking about a particular compound and such, demineralization. So process cycle, it is just summing up what we looked at earlier. First, we are going to look at the example, I guess, of calcium and magnesium. I want them to be removed, right? What is going to happen when it contacts the resin? Due to the greater affinity, calcium and magnesium are now ion exchanged or are adsorbed onto the relevant resin, while Na plus is exchanged. We have ion exchange, let us say, right? After the capacity of the resin has been reached, meaning there are no more available active sites, right? Then what do? We can't remove anything and breakthrough has occurred, right? Breakthrough of Mg2 plus and then Ca2 plus. So resin is taken out and then regenerated with concentrated NaCl. As we know, it is like a reversible reaction. So the greater the concentration from one side, you are going to follow Le Chatelier's principle and it is going to move in the other direction. So more regenerant is not ideal. Why? Okay, we will come back to this. Okay, why? Here it is higher cost, but if it is more regenerant or more concentrated, more effective regeneration. But we have to balance it out with the needs of higher cost, let us say. Or if typically we look at counter current, right? Counter current as in this and this direction. So that is counter current and reuse of the regenerant. Again, as mentioned, these cases of ion exchange and such, all these are fine. But those are, there are a few people who look at, degradation, ion exchange and then degradation on in situ. Why is that great? Because right now what are we doing? What do we say, having NaCl and then regenerating the relevant solution. Fine. I have now, what do I have? I have a lot of NaCl, fine, and let us say I have my what do we say, high concentration of calcium and magnesium. Fine, these are not very toxic, maybe that is fine. But if I have let us say lead, right, or mercury, then after regeneration what do I do with it? So the key issue is that ion exchange adsorption, we are only changing the phase of the compound from aqueous phase to the solid phase or adsorbed onto the resin. But we still need to look at the disposal cost, so that is something to keep in mind. Let us move on. So strong acid, right, strong acid resin, right, that is what we have, and it now exchanges calcium with sodium, that is what we see out here. Weak acid too, I guess, but again here a greater operational range of pH, relatively limited. Why? Because it is weak acid and we have to look at the operational range based on the pKa, right. So strong base, OH minus, Cl minus exchange, weak base, I guess, right. So again you can have different kinds of weak base, it is kind of an exchange here. Let me move on. Exchange and regeneration. So it is a reversible reaction, right. It is like A plus B goes to C plus D. A is the resin with Na plus, C is the resin with Ca2 plus. So, if I want to move it in this direction, what will I do? I will add a lot of D, right, and then rather than going in the forward direction, it will go in this, right. So, it is not a reaction, but that is the principle here. Direction of the reaction is reversible, the Chatelier's principle. By applying high concentration of the ion, regeneration process occurs, right. We looked at this. So, we have this, right, this is my resin and it is exhausted, I want to regenerate it. What do I need to do? I am going to regenerate it in this way. Okay, fine, I guess I should have added this. If I want to go it in this way, I am going to have NaCl addition. So, sometimes obviously we are also going to look at HCl regeneration. This is something we have also looked at earlier, let us say. So, different aspects to keep in mind. One aspect is also moisture content, because swelling occurs depending on the size of the ion that is adsorbed or desorbed, right. So, that is something to also keep in mind. So, backwash rate and such, just relevant aspects here for cation exchange resin, the relevant capacity. Keep in mind that we are always looking at equivalents, right, equivalents. So, that is why here I guess we have units in terms of as CaCO3. So, backwash rate is one aspect, and how long? Yes, as you can see, bed expands by percentage. This is something that I mentioned, and regenerant typically used and such, let us see. Okay, so, I guess with that we will more or less wind it up, wind it up. Design consideration. Whenever we look at small examples, size of the exchanger, right, how much is the size of my exchanger, what is it going to be depend upon? I need to know what is the total mass of the compound of interest that is coming in, what is the mass of the compound that my particular ion exchanger can take up, right. So, it is the amount of the exchanger material. How do I calculate that, or why is that necessary? It determines the time for breakthrough, right. So, we convert all concentration to equivalents, as equivalents or with respect to CaCO3, and time to breakthrough, right, total exchange capacity of the bed by flow of hardness. Here we are talking about hardness obviously to the bed, right, total capacity by hardness coming in per time. That will give me an idea about the time to breakthrough, let us say. And what about the total exchange capacity? That is going to be equal to amount of resin into specific exchange capacity of the resin, right, that is pretty much obvious. So, trade-offs, if it is relatively large, longer run time, higher capital cost, right, but lower operating cost. Small, obviously it is the other way around, right. Okay, so with that we are done with ion exchange, and we will move on to looking at or discussing reverse osmosis in the next session. With that I will end today's session.